So today we're going to talk about selection sort. We've actually discussed this before, but now you know more, so this should make even more sense. We focused last time on the algorithm and how it actually works. This time we're going to incorporate the code that you need to know for the AP exam. You don't need to memorize the code. Essentially, the way they're going to ask the question is they'll present you with the code, not tell you what it is, and expect you to sort out what they're asking you to do. So they'll, give you some data and said, what's the end result of running this code? Well, if you could recognize that this is a selection sort, you could just follow the algorithm instead of tracing the code. And following the algorithm is a lot easier than it is tracing the code. So they'll say, what's the result of the list after 5 times through the loop? So it's not like they say, hey, what's this list in order? No, they'll ask you where the list is after going through it 5 or 6 times. So you might have to go through it 30 times to get it all the way sorted. So they want to know partway through what's the list. So you really have to follow the algorithm to get that answer. Or trace the code, which we all know takes a long time. So in order to speed things up, understanding how this works and recognizing the code will make answering these questions a lot easier. So the step is essentially find the smallest value in the array. Then swap it with your current position. So the current position is going to start at the beginning of the array. And then we're going to look through the rest of the array, excluding the current position, to find the smallest value. And then swap them. We're going to repeat until... So we're going to repeat until the last position, which sounds like we know exactly how many times we're going to do it. If we're talking about looping structures, when we do this, there's really only one type of loop that we know exactly how many times we're going to do it. So we have to go through the entire array on an inside loop every time, and we're going through the entire array moving the current position every time. That sounds like 2 for loops. Selection sort, the code has 2 for loops. That's your identifier. You see 2 for loops, it's going to be a selection sort. Here's what it looks like in terms of numbers. So we start with the first index, find the smallest value in this list, which in this case is 1. And then we swap the position. So the 1 goes to the front, the 8 goes here. Now we move to the next value. We're shorter in the list. We know the front of the list is already sorted. So we're now moving along. So that outside loop is moving the green box. The inside loop goes through the numbers that are remaining in the list every time. So we're now at the 5, find the smallest value, that's the 3, swap it. Move over. So we're back to the outside loop, moving the green box over. The inside loop goes through these 3 elements, finds the smallest value, brings it to the front, swaps it. Again, outside loop, moves the index, swaps, moves, swaps. When we're done, it's because this green box has moved to the last position. The code for this looks like this. This is the code block that the AP exam will use. So they start with a for loop. That is the length of the list minus 1. Why do they have to go minus 1? Well, because this inside loop starts 1 value after that point. We're starting that way because if you go back and look at this, this is our swapping value. So we're not including this in the search. We're assuming that the front half of this is already going to be sorted. So we're always going down by 1 more. We're inside loop is going to be 1 more. If we did not subtract 1, when we got to the end, we'd walk off the edge of the list. So that subtracting 1 there is important. Fortunately for you, though, they're giving you this code. So even if you forget the fact that you have to subtract 1, that's okay. You just have to recognize this is a selection sort because it's 2 for loops. So you need to go home, Memorize. Selection sort. 2 for loops. That's it. Really straightforward. Look at the code. Now, as soon as you recognize that the selection sort is in front of you, you follow the algorithm. The algorithm's pretty straightforward. Go through the list, find the smallest value, swap it. Go through the list, find the smallest value, swap it. Memorize the algorithm, and you're good to go for a couple questions. They'll be very easy questions to answer, because then at that point, you're just following this algorithm all the way through. Here they're checking the number of comparisons. They're counting comparisons. So maybe they can ask you the different ways at getting at this information. They can say how many comparisons were made by the time you get to the 7. Or by the time you've gone through this 3 complete times. So that will put you at the end of this, how many comparisons were made. Or they might say, what's the state of the list after 3 complete loops? 3 complete times through the loop. So they're going to ask the question in that way, and if you're just following the algorithm, that's pretty easy to write down the answer to. If you're tracing it, that's a lot harder to do, because you really have a fairly complicated trace table if you're following 2 loops. You got a lot to keep track of. So I think it's easier to memorize what a selection sort is, memorize the algorithm, memorize that it is 2 for loops. And that's pretty much the nuts and bolts of the whole thing. So what I thought I would let you do is just take a minute and see if you could practice this algorithm. See if you can go through and sort this out. These are the indexes down here, 0, 1, 2, 3, 4, 5. These are the actual numbers. See if you can run through the algorithm. Because once you memorize what the code is, running through the algorithm becomes the most important part. So I'm going to pause the video here. I'd like you to go ahead and try to do that, and then we'll go over the answer. When we start this trace, we're starting here at index 0, and we're going to go through and make n-1 comparisons, right? Trying to find the smallest value in the list. So we store the value, first store the value 79, and then check 64 and 79. Is 64 smaller than 79? Yes, it is. Then check 64, and then 67. Is that smaller? Then check, and so forth and so forth. So it's n-1 comparisons because you're 1 less than the current value. You're taking off that first value, because that's just going to get swapped out. We don't really even care what this is. We're looking through the rest of the list to find the smallest value in the list. So this n-1 is listing the number of comparisons. The smallest value in the list is 12. So our new list, we swap these two, and the 12 goes in front. And then it's 79, 64, 67, 56, and then the 21 is now here. Our current index now moves over to the next value, and we're going to go through and sort this list, which is now n-2. So we go through and find the smallest value. Turns out the smallest value is 21. Swap them. So we're going to now do the 12, the 21, the 64, the 67, the 56, and then this is the 79. So we're always swapping that. Move our index to here. We're now at n-3. Find the smallest value. It's the 56. Swap them. So we are at 12, 21, 56. Excuse me. $67, $64, $79. Remember, don't put it at the end. It swaps position. So the 64 and 56 swap position. So we're going to go through now. We're at n-3. So this is our new spot. Go through the list. It's going to be a really short trip. Find the smallest value. It's 64. Swap it. So we have 12, 21, 56, 64, 67, 79. Now visually, you're probably looking at this, oh, it's already done, it's sorted. The computer can't do that. The computer actually has to continue sorting it. Even though we know this is sorted, the computer won't be able to not skip this step. So we have to go through and follow the whole process. It's n minus 3 comparison, excuse me, n minus 4 comparisons. There's only one value. Find it, swap it. Actually, we don't swap because 67 is not smaller than 69. Okay. So that's it. Move one more spot. Actually, no, I'm sorry. We do swap. 79 is the smallest value in the list. Sorry. Swap it, and then we'll have to swap it one more time. My fault. Yes, no? No, that's right. Okay. No, it stops right there. 12, 21, 56, 64. Hang on, let me double check that. I think 12, 21, 56, 64, I believe it does swap. 70. No, that wouldn't be right. No, it doesn't swap. 64, 67. Again, we're indexed now down here. 79. That's it. Nothing else less than the list. The list is sorted. Yep. So again, we do include this number when we're looking for the smallest, the 64. We're looking for the smallest, 67. It just so happens in the last iteration, 67 was smaller than 79, so we didn't do any swap. So we're going to have you try it one more time. I'm going to pause the video and have you trace this loop. One typo fixed. This was supposed to be n minus 4, not n minus 3, which shifts all these, and then when you do your subtraction, you get 0, 1, 2, 3, 4, 5. Okay, so let's take a look at that code. Oh, step 1, we start at n minus 1. Starting at the 67, we're looking for the smallest value in this list, so we have n minus 1 comparisons. Smallest value in the list is, boom, 24. Swap those, put the 24 in front. Rewrite the rest of our list. The 24 is now a 67. 50. Our green box is now here, 46. So this is going to be interesting, because now when we go to look for the smallest value in the list, we'll see that it is 46. There's no swap needed. 46 is the smallest value in the list. So we're going to go ahead, no swap gets necessary. In fact, if you want to kind of show that, you could show like a red box right there. And we do 24, 46, 72, 62, 67, 50. Our green box is now moved to here. So we're going to look for the smallest value in the list. Smallest value in the list is here, the 62. Rewrite our list with our swap. 24. Oh, it's the 50. My fault. Just making sure everybody's awake. The 50. Here we go. 24, 46, 50, 62, 67, and then down here is 72. Okay. Our green box is now moved. We're on the 62. So it turns out, again, our target is also where the index is. The 62 is the smallest value. So you can think of it swapping it on itself, if you want to think about it that way. It swaps to the same position, which is really doing nothing. But again, in code, it doesn't really matter because we're not really tracing the code here. We are tracing the algorithm. And as long as you have some symbolic way of representing this, it's fine. 67, 72. We're going to go through those same position swaps 2 more times. 24, 46, 50, 62, 67, 72, there's our index. Nothing to swap with. We're at the end of the list. It's sorted. Right? N is equal to 0 at this point, so here's our sorted list. Now, what's interesting is that if this list is already sorted, you might have kind of guessed this, it's still going to take the same number of comparisons. It still has to look through the whole list. It doesn't know that the list is sorted. So this is not going to change. This is still going to have the same big O notation. It's not going to change. It's considered n squared. So it's going to be the same thing every time. Whether the list is sorted, whether the list is not sorted, whether the list is in reverse order would be the worst sort. If it's counting down, that's the worst sort. Or if it's in order, that's the best sort. Doesn't make a difference. Always going to be the same because it's a for loop. It's counted on the length of the array. Has nothing to do with the values that it's finding. The only time you see a difference in a sort that has some flexibility depending upon the size, not the size of the list, but the sortedness of the list is when there's a while loop. There's some type of condition to stop the sort from happening. Here, we're just going through the length of the array both times. So we go back and look at that code. We can see that no matter what, we're always going through the elements.length minus 1, so we're starting at n minus 1. And then on the inside loop is always going to go through the starting at j plus 1 to the end of the list. So we're going one more. Down here is our little swapping procedure. Notice this happens no matter what. Even if we're on the same element, right, this swap happens. So it's swapping on itself at certain points. Here's where our comparison occurs. We're checking to see if element k is less than the minimum index, which is where our current green box was. If it was, then the minimum index becomes k. If that never happens, then the minimum index stays what it was originally, the original green box. That's why we see it swapping on top of itself. The code doesn't care whether it's a different box or the same box. It behaves exactly the same. So at points in the code, like here, it's swapping on the same spot. It's still doing the swap, which is a little weird. It's still doing that temporary thing. You would think that if you could put an if statement in there, maybe to make it a little bit more efficient, but it's not worth it. You don't gain enough efficiency because you're actually adding another comparison rather than an assignment. And a comparison is going to be more, I guess, more memory intensive than just a simple assignment. Assignment, just moving stuff around. A comparison, you actually have to do some logic. So that's going to require more work. So yeah, we do the extra swap anyway. We don't need it, but we do it anyway. So that is the selection sort. There is a exit ticket, I believe. Exit ticket for you to do. There's also a link to some sample code that'll essentially allow you to trace through this loop. You go back to the first. You can see there's 122 steps, but this makes it a little bit easier. If you were going to trace this code out using, rather than knowing the algorithm, if you're actually going to trace it, this is what you'd have to do. You have to keep track of all these values. 122 steps. So if you're writing all of this out in a table, you would need 122 blocks in your table. This is why I'm encouraging you to learn the algorithm and do it that way and trace it. Because if you look, even though we had like 10 steps maybe, what do you have? Count that as 1, 2, 3, 4, 5, 6, 7 steps to go through. As opposed to tracing the code, which is 122. It's definitely more efficient to know and recognize the algorithm and then just use the algorithm as opposed to tracing the code. So if you're not going to listen to my advice and memorize the algorithm and memorize how to recognize the algorithm when they present it to you, then you're going to end up tracing code. Yeah, you can get to the right answer, but it's going to take a much longer time. 122 steps compared to 7. So that's it. We'll get into the next lesson. Never stop coding.